Today we're going to present our group project for subject Communication and Computer Network. This is my team members, Nicole, Sylvia, Clary, Aina, which is myself, and Nur Shazira. Part A, ARQ Protocol Performance Analysis. ARQ works as an error control method in communication system. Main component of ARQ protocols is to detect errors, maintain data integrity, and manage requests for restoring data loss. Because of ARQ, data is transferred properly, so application like money transfer, online lesson, and remote jobs, and real-life messaging are not affected. So next is the importance of flow control in networking. Firstly, it regulates the data transmission speed, so various devices can process slower or faster or even more faster. Without a flow control, a sender capable of high rates may overpower the recipient in the stream. Flow control also ensures that the receiver indicates that it is not ready to receive any further data. Lastly, flow control also enhances the network efficiency and provide preserved integrities of data, and it provides reliable communication.
A very good day, everyone. Today I would like to briefly explain about stop and wait ARQ, which is one of the basic automatic repeat request ARQ protocol used in communication system. Stop and wait ARQ is a simple and reliable protocol used for error control in data transmission. The main idea is that the sender sends one packet at a time and then wait for acknowledge ACK from the receiver before sending the next packet. Let me explain the process step by step. First, the sender transmits a packet to the receiver, then the sender then wait for an ACK from the receiver. If the sender receives the ACK successfully, it will proceed to send the next packet. However, if the ACK is lost or the packet itself is lost or corrupted, the sender will retransmit the same packet after a timeout period. This process continues until the sender successfully receives the ACK. Okay, next slide. We have the simulation that we already done. For ideal network, it has very low transmission, high throughput, and has high bandwidth utilization, and also fast transmission time. And for the congested network, it frequent retransmission due to high loss, and it has low throughput, bandwidth underutilized, and has longer total retransmission time. And next, we have high latency and varying network. With times up is less than latency, the ACK not received in time, and unnecessary retransmit. High retransmission count and low throughput, high overhead.
Today, I will explain the basic of Go Back and ARQ protocol, which is a sliding window protocol designed for reliable data transmission over network. The sender can transmit up to n frames continuously without waiting for acknowledgement X for each one. The receiver on the exact frame that arrived in order. If it gets an out of order frame, it discards it. If a timeout occurs because an X is not received in time, the sender goes back and retransmits the lost frame and all subsequent frames in the window. Here, simulation parameter for window size n is optimized to balance throughput and avoid unnecessary retransmission. Timeout interval determines how long the sender waits for an X before retransmitting. Packet and X loss probability simulate real network unreliability, helping us understand performance under different conditions. In ideal network with low loss, Go Back and achieve about 3 times the throughput of stop and wait because it pipeline multiple frames. In network with high latency, like 100 millisecond delay, Go Back and maintains good throughput while stop and wait suffer significantly. However, when packet loss is high, around 15%, the efficiency of Go Back and drop due to redundant retransmission. Go Back End can waste bandwidth in noisy channel because it retransmits many frames after a single loss. Stop and wait is simpler but performs poorly in high latency network because it waits for an X after every frame. Low scenario for Go Back End performance is high, meanwhile stop and wait performance is low. High packet loss scenario for Go Back End performance is moderate, meanwhile for stop and wait performance is low. For high latency scenario for both is good. As you can see, Go Back End generally outperforms stop and wait, especially in low loss and high latency environment. But in very noisy channel, its performance advantage diminish. To sum up, Go Back and ARQ is an effective sliding window protocol that improves throughput by sending multiple frames before waiting for X. It works well in most network condition but can be less efficient when packet loss is high. Understanding this trade-off helps in designing better communication protocols.
Now I'm going to explain about selective repeat. Selective repeat protocol, or SRP, is a type of error control protocol that we use in computer networks to ensure the reliable delivery of data packets. Selective repeat uses a window-based flow control mechanism to ensure the sender doesn't overwhelm the receiver with too many packets. So here is the difference between selective repeat, go back, and stop and wait. Let us see from the aspect number 1, which is sender window size. For stop and wait, the sender window size is 1, while for go back and selective repeat, the sender window size is n. For the second aspect, which is acknowledgement type, for stop and wait and selective repeat, both acknowledgement type is individual, while for go back and the acknowledgement type is cumulative. Let us move on to the third aspect, which is retransmission. For stop and wait and selective repeat, both have a number of retransmission is 1, and for go back and the number of transmission is n. Now let us see for the last aspect, which is efficiency. For stop and wait, the efficiency is low, while for go back and the efficiency is medium, and for selective repeat, the efficiency is high. Now let's move on to the next, which is pros and cons comparison between these three ARQ protocols. So for the pros, for stop and wait, it is very simple to implement, and it is also minimal memory and processing requirements. For go and back is better efficiency than stop and wait and more simpler receiver logic. And for selective repeat, it is highest efficiency, only retransmits loss or corrupted frames, and better performance in high loss. While for the cons, for stop and wait, which is very low efficiency and poor utilization of bandwidth in high latency network. While for go back and retransmits multiple frames even if only one is lost and not efficient in lossy condition. For selective repeat, the cons is it is more complex implementation and requires more memory or both sender and receiver. As shown in table above, selective repeat offers the most efficient retransmission strategy by only resending individual loss frame. Now let us talk about network configuration for selective repeat. For the simulation setup, we use C++ code to simulate the configuration for selective repeat. This tool allows us to create a virtual network environment and test how the protocol behaves under different conditions. As you guys can see on the table below, there are 4 cases based on key configuration parameters. Let's move on to the next, which is network scenario and simulation execution. For first scenario, which is low packet loss and high bandwidth, this scenario serves as a baseline to measure how both protocols perform when there is minimal interference. As expected, both protocols operate efficiently and achieving high throughput with little to no retransmission. Now let us move on to the next scenario, which is high packet loss and low bandwidth. This condition reveals the key difference between the two protocols. Go back and, due to its design, we transmitted multiple frames after a single loss, resulting in wasted bandwidth. In contrast, selective repeat was more efficient, only retransmitting the lost frame, making it better suited for unreliable networks. For the third scenario, which is high latency with different timeout interval, by adjusting the timeout interval, we observe how premature or delayed retransmission affected performance. Short timeouts causes unnecessary retransmission, while overlap long timeout delay recovery from actual losses. Both protocols were sensitive to timeout setting, but selective repeat shows slightly better adaptability. And for the last scenario, which is varying window size. In stable network, increasing the window size improves performance for both protocols. However, when the packet loss occurs, go back and become less efficient with larger window due to bulk retransmission, while selective repeat continue to handle losses gracefully by targeting only missing packets.
I will talk about ARQ protocol performance comparison. We compare 3 ARQ protocol, which is stop and wait, go back and selective repeat. Stop and wait is the simple, but it's slow and efficient for busy network. Second, go and back. It's perform better, but when one frame is lost, it resend reserve wasting bandwidth. Okay, the lastly, selective repeat is the most efficient because it only resend the efficient lost frame, saving and resource. In our simulation, selective repeat had the highly enough put, which is 1.1 Mbps, and made the best use bandwidth, making it the ideal choice for unable network. Next, I will talk about ARQ performance metric. On this part, we analyzing the performance of 3 ARQ protocol, which is stop and wait, go back and selective repeat. They're using key of performance metric. First, stop and wait. Perform the worst. It sends the most packet and the highest transmission count, which is 18, and achieve the lowest throughput at just 0.2 mph. It's been using the use was poor and it introduced the higher processing overhead, which is 30%. Next, about go and back. This silently better with the paper transmission and a moderate throughput of 0.6 Mbps. However, it still wastes bandwidth because then we sending multi-frame after a single loss. Lastly, about selective repeat of performance board. It had only 3 transmission out of 45 packets sent and achieved the best throughput at 1.1 Mbps. It also made excellent using of available bandwidth at 85% and keep processing overhead low and only 7%. To summarize all of 3 ARQ protocol, selective repeat is clearly the most effective and reliable choice and efficiently for network that experience packet loss or high latency. Next, I will talk about critical implementation of simulation result. We're using different ARQ protocol based on simulation result. First, in the table work with the low packet loss and high bandwidth. All 3 protocol we using, which is stop and wait, go back and selective repeat. 3 protocol is performed well. However, go back end is especially suitable for environment like LAN or river network with minimal interface. Next, about unreachable or low bandwidth network. Go back end become inefficient due to bulk translation. In this contrast, selective repeat is much more efficient because it only presents low packet, conserving bandwidth and improving reliability. Okay, about highly latency and eventually timeout interval. This part is make a go back struggle due to sensitivity to timing. Meanwhile, selective repeat adapt better and maintain stable performance. It's making ideal for real-time application such as VoIP and video streaming. For the lastly, in test solving different window size, go back and server from increased transmission
Part
overhead
B.
as the
Practical
window
Network
grade.
Design for
Selective
Narni
repeat,
Sundarian Berhad.
however, remaining efficient and stable, making it the best choice for scalable or mobile network environment. In summarize, the choice of ARQ protocol should depend on the network condition, but if efficiently, adaptation and high performance are prioritized, selecting repeat stand out as the most suitable option.
The objective for this network design is to have a secure and dependable system for offices, so it can connect employees within the company without problems. This network design suggests the company to establish a network that uses both wired and wireless technology. So it can connect by using Cat6 Ethernet if they are in the same building, and using fiber optic cables if their offices are further from each other. So this is the example of topology that we use, which is star topology and bus topology.
Next, I would like to explain the network topology chosen for our project, which is hybrid topology that combine both star and bus configuration. In our design, we have selected a hybrid topology that use star topology within each floor and a bus-style backbone to connect all the floor through a central router. This combination allows us to take advantage of both topologies while minimize the weakness. We use star topology for each floor because it offers high performance as each device has a dedicated connection to the switch. It also provides easy fault detection and simplified troubleshooting. If one device or cable fail, the rest of the network remain unaffected. It's also easy to manage and expand in each floor. We use a bus-style backbone to efficiently connect multiple floors using a shared communication line, and also to reduce the overall cost of cabling compared to a fully switched backbone. And it also provides a cost-effective solution for long-distance communication between floors. This bus backbone connects each floor switch to a central router, creating a streamlined and scalable design. By combining these two topologies, we achieve a balance between performance and cost. And also the system is flexible and easy to upgrade. The design is resilient and can isolate fault more effectively. It provides high performance on each floor while keeping the interfloor connection simple and affordable. In conclusion, the hybrid topology is the most suitable choice for our project because it offers performance, flexibility, easy management, and cost effectiveness.
In this section, I will present the key networking device selected for NAMI SDN BHT. Each device has been chosen based on its purpose and specific justification to meet the company networking needs. The router connects the company office to the internet service provider and routes traffic efficiently. It supports advanced features like blunt quality of service and security, capable of handling 500 Mbps downlink and 300 Mbps uplink. It also includes firewall and VPN functionalities to secure the network. Managed switches are used to connect via device within the office. They provide gigabit Ethernet with power over Ethernet (PoE) to power devices like phone and cameras. These switches support VLAN segmentation and QoS, ensuring scalable and reliable network performance. Wireless access point provide Wi-Fi connectivity for employee and guests. The selected WIP support dual band frequency and the latest Wi-Fi 6 standard. They offer multiple SSIDs to separate secure employee access from guest network, enhancing security and performance. The firewall is critical for network security and access control. It performs the packet inspection and intrusion prevention to protect the internal network. Importantly, it maintains security without causing network slowdowns. Print server manages share printer centrally. This setup reduces network load by efficiently handling print job and providing easy access to printer for all users. Last but not least is network attached storage or file server provides centralized data storage and backup. They facilitate file sharing across the organization and support disaster recovery strategy to protect critical data. This device collectively ensure a robust, secure, and scalable network infrastructure for NARMI SDN BHT. Each device is carefully selected to meet specific operational needs from connectivity and security to meet data management and user access.
For NARMI scenario per hat, we use a classy private IP address space, for example 192.168.10/24. This means they can use up to 254 usable IP address. The network is divided to serve different parts of the organization, which is Office A, Office B, mobile user, guest Wi-Fi, and infrastructure such as router, switches, or server. The divided rectangular block is subnetted into smaller chunks to improve performance, add security, and control traffic better. We also using VLAN configuration to logically spread and manage traffic more securely. They use VLANs or virtual LANs. This setup isolates traffic between departments, exchange security, allows better bandwidth management, and support role-based access point. In summary, to manage the network at NARMI Sendirian Berhad, we divided a classy private IP block into smaller subnets for each department and service. This helps in isolating traffic, improving performance, and applying security rules easily. Each group gets its own IP range, and VLANs are used to logically separate them even if they are using the same switches.
In this section, I will present the key component of our proposed network security plan. First, with the security architecture, which is built on a multi-layer different model. This includes wireless, firewall, IDS or IPS system, VLAN, endpoint protection, encryption, and SIPM, increasing a strong perimeter and internal security. Next are the key measures we implement, which is firewall to control traffic, VPNs to insecure remote access, and intrusion detection prevention system to monitor and block threats. For access control, we apply role-based restriction, prevention, guest Wi-Fi from the main network, and use make filter with capture portrait for physical authentication, and usually only choosing user can connect. Next about monitor is done through SNMP and NetFlow, which is for help us analyzing traffic and detect anomalies in real time with alert and login system. Under backup and recover, we perform routine backup, analyze of site storage, deliver reduce system, and have a clear prediction for fast recovery, ensuring business continuity. The justification for this plan is that it cost effect, scheduled, and compliant with international standard like ISO 27001, while providing strong data protection availability. Finally, our deliver include the complete security architecture diagram slide, explain each component and directly this application slide. Thank you. That's all.